Okay, here we go. Tell your neighbor. Correct answer is B, the same. Okay, does not matter how you draw this Gaussian surface, the enclosed charge is still enclosed. Okay, so it doesn't really matter even how you draw your Gaussian surface. It's going to have the same amount of flux going through. Good with that?
How would it change when you put the charge on the surface instead of outside or inside?
Here's my best stab at that one. You don't. This Gaussian surface is like a tool, so we're not gonna try to like break the tool, if that makes sense. So if you wanted to include look at the surface, put the surface right inside the Gaussian surface, if that makes sense.
Yeah.
Pick all that are true. Have a conversation.
Oh, you know it's B. How could be a C?
Yeah.
Plus what?
Correct answer is B and C. You good with that? Does everybody, this makes sense here? The red is not at the center, but it has the same flux. Okay. Tell your neighbor. Correct answer is D, 0. Okay. There we go. It's inside a conductor. Let's see. Do I want to do this? Let's see. What do I want to do? We're going to try it this way. Tell your neighbor. Okay, maybe I should have. Okay, so here, if we did the Gaussian surface, the charge resides on the outside. There's no enclosed charge, so no electric field. Okay, that's one way to look at it. Another way to look at it is, if there was an electric field, electrons would move until the net electric field is equal to 0. So like this would be, this creates its own electric field, okay, going outward. And this polarizes, creating its own electric field that counteracts so that the net electric field is equal to 0. When we do Gauss's law, it is the net electric field. There might be multiple electric fields present, but the net electric field would be 0. You all right with that? So here, if we did our Gaussian surface, what did you say the answer was? Good. If we did our Gaussian surface here, the flux, or we'll just start here, the field is 0 because you're on the interior of a conductor. So you know that the net charge has to be 0. You have a positive in there. So this charge has to be equal to negative that to make the enclosed charge 0. Good? Okay. Sorry, this slide seems overwhelming. What is the difference that I'm saying? Tell your neighbor what you think. Because the charge distribution can be wrong. Yeah, okay. So, correct answer is B, it is only the electric field from this that cancels out the red. Okay. Oh, that's the difference. See how it's congregated here, clustered here? Okay. And here it's equally spread out. There we go. That's what I did. Okay. It is only due to the electric field created by this negative distribution of the charge on the interior. That's what cancels out this. You all right with that? Huh, man. I like told you all the answers. All right. Did everybody go with B? So disappointing. All right. And there's me telling, okay, I'm not sure. All right. So it's just these two fields cancel each other out. I don't even worry about what's going on the outside here. Good with that? All right. Thumbs up when you got a guess. Tell your neighbor and tell them why. Correct answer is A. If you do a Gaussian surface around here, the total charge enclosed would be plus Q. This is negative Q. This whole thing's neutral, so this has to be positive Q. Good? You're thinking Gauss's law, is this making sense? Like how this all flushes out here? So here they're clustered here. Here it's equally spread out. There, it's clustered over there. Tell your neighbor. Everybody good with B? Equally spread out. Okay. Yeah. Okay. Yeah, we'll just keep going this. All right. So. Thumbs up when you've got something. Tell your neighbor. Correct answer is B. Okay. So, do you remember the first question? That one. Okay, it has the same flux. It's like we don't necessarily know where it's located. Okay. So it's as if a point charge is right there. So this is one aspect of shielding. Okay. Where yes, you know what's going on overall, but you don't know the location of that charged object. Okay, good with that? Tell your neighbor.
Isn't it getting canceled out?
Correct. Oh, sorry, I don't want to impede conversation. This is this like what you're doing right now. This is what you're going to do on an AP test. Student A says this. Student B says this. Explain what you like. You are doing. You are preparing. Correct answer is B. Okay. Here's why. We draw one aspect. We draw a Gaussian surface. Total enclosed charge is Q. Just a circle. Point charge. Well, then you ask yourself, well, what about the electrons? Aren't those like, well, this is like a hollow planet. The net electric field from the electrons, the negative charge is 0. What about the protons on the outside? Well, if they are equally distributed, hollow planet again. Net electric field from the protons out here, 0. Okay, the only thing we care about is the charge enclosed. How we doing? Good? Okay, so let's change things up. Let's put the positive thing off-centered in that cavity. Thumbs up when you have a guess. Tell your neighbor. Correct answer is still A. If you have your Gaussian surface, electric field in the interior of the metal is 0. So we have the same conversation. Tell your neighbor.
Even if the fields are right, like,
Why is he
Correct answer is?
Correct answer, Rufus.
All right, so check this out. You ready? So, the electric field is stronger here, right? Because it's closer, and weaker over here from the positively charged particle. Okay? These electrons are solely responsible for annihilating that red electric field. So, they must be more concentrated here to cancel out that stronger electric field and more spread out there. B. Does that make sense? Okay. These are solely responsible for canceling out this red field inside here. Not, oh, bad. Sorry, that was completely wrong. This is the right answer. But the way I drew it was horrible. Okay. Sorry. This electric field inside here is the red. It's not canceled out. It's canceled out. Sorry, that was poor teaching. Bad teacher. Okay. What this is canceling out is this electric field here. Inside the metal. You okay with that? Okay.
Unless you're using my face.
What is the first one? Switch it back to the other one.
What?
Circle, right? Massage. Like that. So, because it's not, it's only like circle. Yeah. It's just, how?
The field is canceled out. Only by the outside has to be.
A.
And write that down. And there would still be a field.
But there's still field.
There wouldn't be a field. Or there would be a field.
Correct answer is A. Okay. This one solely cancels out that guy, the electric field in this. So this charge is uniformly distributed. Okay. So that's one aspect of shielding. When you look in from the outside, you can't tell what's on the inside. Okay. Tell your neighbor.
Whatever you say, guys.
Okay, so is everybody good with this? Polarizes. So the net electric field is 0 inside the conductor. Now, let's say we carve a hole cavity in our neutral metal sphere. Correct answer is B. Okay. Josiah.
So there's not any charge in the metal, with or without the cavity, there's not any charge in the metal, right?
Correct.
So, never mind, actually.
Does that mean like at every single point inside the metal, no matter if there is a metal at that given point, there's no field at that field?
Right. Okay. So everywhere in here, the electric field is 0. Okay. You right with that? So how the charge distributes on the outer part is solely responsible for canceling out the electric field that's produced on the outside. And this is the other half of shielding. Okay, so this is why when you have electronic components shipped to you, they arrive in these plasticky metallic packaging. So if there's some kind of static buildup, it's okay. It's on the inside. It doesn't see anything that goes on the outside because the outer surface shields so that the net electric field on the inside of it is still 0. Good with that? Okay, so let me define what the original scenario was. The original scenario, let's see, hold on, let's see. Now is second charge. Okay, we're going to start with, where are we at here? Sorry. In the middle. We're going to start with this scenario here. Okay, that's our original scenario. And then we bring in Q2. Tell your neighbor. Correct answer is false. Okay, you're still going to have this electric field produced by this dude. Okay, this polarization on the outside cancels out the field that this guy produced inside the interior here. So this one produces its own electric field, but is unfazed, unaffected by the electric field produced by this one because this outer surface negated stuff on the inside. So in here, so
Alright, if you just have a really, really powerful external or internal charge, could it override that whole shielding thing? Like, we just say Q2 is
no.
functionally infinite.
That would cause arcing, and then it wouldn't be static anymore. It would be, you'd have a current.
Infinite
Like,
charge.
yeah, kind of because it's going to pull stuff out of the air to make that, like, the fact that you have an electric field, like,
So it's just valid until you get a charge powerful enough to cause a current.
yeah. Okay, correct answer is false. Okay, it would stay the same. What about so this is asking about just the numeric value, not the arrangement, but the numeric value. We started with just Q1 in the middle and then brought Q2 in. Would the total surface charge change? Tell your neighbor.
Q1 was already, and Q2 is sure no. I think if you somehow shove Q1 in there, then I think it would. Because, yeah, because Q1 would result in positive charge along the side. Net positive.
Correct answer is false. If you had your Gaussian surface like that, the charge enclosed is Q. This thing's neutral. This becomes negative Q. Therefore, on the outside, this has to be positive Q. All right with that? So that the last question was how, like the value of this is how it's would be distributed on that. Thumbs up when you have a guess. Tell your neighbor.
I'm saying actual birds, by the way.
Correct answer is true. It would have to respond to this to cancel out this electric field so it would polarize. You right with that? So if this was, what did I say? Positive. So you would get this polarization effect. It would look a little different with or without this, like there'd be a higher constant, there'd be more positives on this side and less, there'd still be negatives, but there'd be less, overall it'd be positively charged. Okay with that? And please also keep in mind that this is a very small fraction of the electrons shifting. Okay, there's hordes of them. Like, so we started with this with the plus Q, and then we brought Q2 in. Does that change the electric field outside the conductor? Tell your neighbor.
I'm showing the eyes of the external charges.
Okay, correct answer is? Yes, true. You've got this one's originally creating it outward, and then you bring this in, you've got two electric fields overlapping. That's going to change the net electric field outside, but not on the inside. Okay? Ooh, sorry. Let me just quick time out while I came to this. On the free response, I would do it backwards in terms of how I listed those. Like do the oldest test first. They get harder as they get more closer to 2024. Like start with the oldest test first and go chronologically in that order. Okay? My recommendation. I mean, you could just go for it if you wanted to, like, but correct answer is A. Good with that? Okay. Tell your neighbor. Correct answer is C. Okay, it's just this thing. It's just this. Yes? Okay. Tell your neighbor.
Pretty sure due to the whole shielding thing.
Correct answer is
And the ball overall.
very good. They attract. They're absolutely charged. They attract each other. Yes?
Okay, that's what I was thinking.
Okay, they attract. Coulomb's law. You just use straight away. Okay? Good with that? I mean, that's the equation you'd use. All right. Oh, what am I doing? I'm gonna trust what I know what I'm doing here. All right. Tell your neighbor. There we go. D. I'm not sure. Oh.
Two questions ago on the one where you said they attract.
Yep.
If the field in the metal and in the pocket, if the field in the metal is 0 and the field in the pocket is just relying on that one charge.
Yep.
Why does it have a force on it?
Because the outer shell has a charge on it.
Or it's experiencing.
Okay, so it's just experiencing the force of the outer shell moving.
Hold on to that thought. Correct answer is? Correct. A is correct. Yes? Yes. It's just the inner surface that's canceling out the electric field created by the center through the metal there. Like from this edge outward. This is what is canceling out that field. Good? Correct answer is dangerous dinosaurs. Yes? Correct answer is have a conversation. I heard different letters. Find someone you disagree with.
Oh, I didn't. Oh, I didn't see that. Gravity shield?
Correct answer is? Correct answer is D. Dangerous dinosaurs. Okay, I don't know. Yeah, this. Hold on, 1 second. One momento. All right, I just need to create a slide. All right, what happens if this is free to move? I do not know why I didn't ask this question. This is a great question. So we said that this is being forced to the right and this is being forced to the left. If it was free to move, so bad. Would this option A, you see where I'm going here? Option A would be here as this moves, it progresses like that. Should draw it over here, but I don't have any room. Option B is that stays stationary. Option C and this one moves. This is both move. And this one is just this guy moves. And this one stays at rest. Does that make sense? The answer is correct answer is B. Okay. Yes. No. Does that make sense? Like this is the gold part's what feels the force. Okay. This goes until what happens though when this touches that. If this is a conductor, right? This is a conductor. This becomes positively charged on the outside. And the inside, this becomes part of this conductor. And therefore, chew on that. We'll talk about that tomorrow. Yep.
You said the answer to this question here was A.
Yes.
So then, like, if there's a force to the left, like, why wouldn't it?
It only acts on this part here.
Okay, but that's not the charge, though. So then would the answer to that question be D?
Oh. Fair enough. All right. All right. Sorry. If you were, I might have misread this question. D, if you're considering, which it does say that, the electric, yes, sorry. D is the right answer for this one. There's a force on the gold part. Sorry, good call. Woo!